Hi, let's take a look at this equation. Equation number 7. This is an acid-base equation, and this paper was done in February-March 2016. I just want to take a look at this particular equation and just to make sure that you guys are on par in terms of what's required of you as far as these questions are concerned. We'll cover more than what's in the question, but also I will be highlighting some more information that you may particularly expect when you're dealing with acid and base problems. Just fasten your seatbelt and let's just go through the problem together. The first question requires you to define the acid in terms of Lowry-Bronsted theory. Now, if they want you to do that, what you have to think of is your definitions of acid base based on the both model, Arrhenius acid-base model, as well as Bronsted-Lowry acid-base model. So both the definitions, the different definitions are different based on each and individual aspect of what the scientists intended to achieve with the concept. So let's define acid in terms of Lowry-Bronsted. Now that's 7.1. If we're going to define acid in terms of Lowry-Bronsted theory, according to that theory, an acid is a proton donor, right? So for this first question, what is an acid, or how can we define an acid in terms of Lowry-Bronsted? An acid is a proton donor or H plus donor. So I can say 7.1, there's going to be an acid, is going to be a proton donor, a proton, or maybe stated somewhat differently, you can say a proton and indicate what the proton is. The proton is an H plus ion, and then you can say it's an H plus ion donor or the proton donor. All right, both ways it works. All right, the second question, I've just cropped that out and pasted it here so that we can take a look at it separately from the paper, but I'll keep getting back to the paper. Now the second question, which is 7.2, carbonated water is an aqueous solution of carbonic acid. All right, so when we have carbonated water, basically what we have is a carbonic acid inside water making a solution, which is carbonated water. Now the carbonic acid they've given us here, which is obviously aqueous in solution, ionizes in two steps basically when it dissolves in water, and it does the same thing that the sulfuric acid actually does. Now, if I may give you an example, if we have sulfuric acid, this is the formula for sulfuric acid being added to water. Now the sulfuric acid will dissolve will ionize actually when dissolved in water, and so if it ionizes, in other ways, it breaks into its constituent ions. The ions of sulfuric acid is actually an H plus ion and the hydrogen sulfate ion. So they're going to break into those ions actually in the first reaction. Unless reacted with the base, this is actually what it's going to do. But if reacted with the base, for example, it had to break into H plus and then an HO4 2 minus ion. So unless stated otherwise, if reacted with water, this is exactly what we're going to do. And then if it does break, it's going to give us the H plus ion. Now the proton here will be donated to the water molecule. So if these are separated into those ions, the ion of H plus or the H plus ion, the hydrogen ion, will be donated there, right? In which case we're gonna have the hydronium ion. Now this definition works for both Arrhenius acid base or acid, and as well as Bronsted-Lowry acid. Now in Arrhenius acid is a proton, and Arrhenius acid is a substance obviously that ionizes like it did to give rise to them. All right, but in the Bronsted-Lowry, which I mistakenly said there first in the place of Arrhenius, the Bronsted-Lowry is a proton donor. It gives away the proton. All right, we don't intend to thinking about the fact that it gives rise to that. It just automatically happens. All right, so and then what we'll be left with will be the hydrogen sulfate ion. sulfate ion. The hydrogen sulfate ion has a -1 charge because one proton here that was supposed to neutralize that -1 charge is now donated here in the water to give the hydronium ion. Now in the second reaction, we're gonna have this sulfate ion, hydrogen sulfate rather ion, and that's gonna be reacted again to water, or maybe dissolved in water, if I may. If it's dissolved in water, in this case, it's gonna give us again give rise to the hydronium ion, and then plus. Now you see these ions now are gonna break into H plus and then SO4 minus. Let me just fix my S there. It's going to be SO4 2 minus the sulfate ion and the hydrogen ion. So it's going to break apart into sulfate ion and hydrogen ion, or ionizes into sulfate ion and hydrogen ion. So the hydrogen ion is being donated, as we can see, into this substance right there, water. And then we're going to be left with the sulfate ion. So this is the type of reaction that will happen when this is reacted to water. So it's gonna ionize this in 2 steps. So much like what this is gonna do, right? And particularly, I've chosen to use this one instead of the one that they gave us, and so that you can be able to see what exactly is it that we intend to talk about here. Now, the similarity between these two S's is that both of them have 2 there. I hope you identify what I mean. They have 2 there. The carbonic acid has a 2, and then the sulfuric acid also has a 2. Now, the 2 here represent the number of protons that we have in the substance. So both of them are diprotons, all right, just like this one is. So they are diprotic in a sense. That's the term that we use for them. They are diprotic acids, so because they can donate 2 protons. That's why they're diprotic. So they can donate to H plus ion. That's what they can do. All right. So when dissolved in water, they usually do it in 2 steps. But when dissolved with other, or maybe when reacted, other than dissolved, when reacted with base, for example, they may not do that. For example, if I may react the sulfuric acid with the base of a strong base, the sulfuric acid with the base of a strong base. Let's say I'm choosing the sodium hydroxide. It's not gonna this not gonna break in 2 steps, obviously. So it's gonna be basically neutralized into, let's say we have H plus, and then here we're gonna have SO4 2 minus, and then for this one it dissociate because it's a base into Na plus and then OH minus. Now remember, acid-base reaction gives salt and water. Those 2 are gonna give us a salt, which is the sodium sulfate salt. Now the formula for sodium sulfate is that. All right, so basically we need 2 sodium ions to neutralize the -2, because it's a +1 charge to neutralize the -2 charge on the sulfate. Now, and then these 2 will just basically give us the water molecule like that. All right, so you can see in that case we didn't have 2 reaction of this, only when it's reacted to water. Now I'm going to go back to the equation here. So the reason why that's exactly that is because it's also a diprotic acid, just like sulfuric acid is. All right, now I'm sure you may be familiar with the sulfuric acid reaction from class. Now the equation, however, had nothing to do with all of that, but I'm sure we're going to get something similar to that as we go on. Now we have the 7.2.1 question. They want us to write down the formula for the conjugate base of the carbonic acid. Now, in order for us to do that, we have to know when we react the carbonic acid with water, what exactly do we get? All right. So when we react that with water, it's going to give us, again, that's an acid. This acid will ionize into H plus and then CO3 2 minus. It was supposed to do that, but since we're reacting with water, now it's gonna ionize into that. All right, much like what an acid does with a base, sulfuric acid does with a base, and what it does with an acid. It's 2 different things, so we should be able to spot the differences. All right, Now this is going to give rise to hydronium ion, and we're going to be left with this, the hydrogen carbonate. The hydrogen carbonate has a charge of a -1, while the carbonate has a charge of -2. In the second step, it's exactly what we were going to get. So unfortunately, we're not going to do the second step, but much works like the one that we've done with the sulfuric acid. Now, what they want us to do is to identify the conjugate base of this. Now, this is an acid, and we know this base. Water is a base because it is accepted according to Arrhenius. It gave rise to that. All right. So water is a base according to Bronsted-Lowry. I'm getting a little bit mixed up here. According to Bronsted-Lowry, it accepted the proton. Exactly, that's the definition I wanted to do. This one is an acid. According to Arrhenius, it has given rise to that. All right, appropriately put. Let's go ahead again and just figure a few things. All right, they want us to identify the conjugate of this. All right, now acid-base reactions are usually reversible reactions. So when we have an acid-base reaction, you just have to know it's a reversible reaction. So now we have the acid and the base in a forward reaction. This reaction can be also written in a backward manner. So just to illustrate my point, I'll go ahead and write down this equation in reverse. Now that's what hydronium ion reacting with hydrogen carbonate and to give us water and carbonic acid. Now with this, I just want to illustrate something to you guys. If this is what happens in this reaction, which is a reverse reaction, the second reaction I've written down, you can see we can also spot an acid and a base. Now we could do it even when it was looking backward, but I just feel like it's more apparent when looking this way. All right, now we have an acid and a base in this forward reaction, which is a reverse reaction. All right, so can we be able to spot which one is an acid, which one is a base? When we look at this, it went up to that. All right, so it became the water. In other words, it gave off the proton. All right, so it has given us the H plus, and it was left with what? With water, which exactly that is. All right, and then this one, actually it was H and then CO3, now it's H2, meaning it accepted the protons. No, this proton that left the water molecule, the hydronium ion, to make them a water molecule, it came here to give us that. So this, in a sense, it's a base because it accepted the proton, and this one is an acid because it donated the proton. All right, so we can just label that here. That one is a base, and this one is an acid. So we just need to pair the two. You look here we have an acid, and here we have a base. You pair an acid and a base. That's what we mean by an acid and its conjugate base. All right, so we've paired them. I have this and that, which meaning that this is the conjugate base of this carbonic acid. All right, so for that particular question, we have the conjugate base for the carbonic acid would then be HCO CO3 minus. Don't forget to put that minus charge there because it's important. All right, next question, they want us to write a balanced equation for the first step in the ionization of carbonic acid. I went a little bit ahead of myself because I've already done that. So I'm going to just say this is 7.2.2, the 7.2.1, we've written the formula there as a carbonic acid. Now, let's take a look at the next problem. In 7.2.3, they are saying the pH of carbonic acid solution at 25 degrees. All right, now, when they hint you about that, you should pay attention to what exactly is about to happen. At 25 degrees Celsius is 3.4. So the pH is 3.4. I'm just going to go ahead and write that down. Change that to that. The pH is 3.4. Remember, pH is given by the equation. pH is a negative logarithm of the concentration of the hydronium ion, or you can say your pH is going to be given by a negative logarithm of the concentration of the hydronium ion if you don't want to put the hydrogen ion. So it can be the hydronium ion or the hydrogen ion. So this is the hydrogen ion, and this then is the hydronium ion. All right. Okay, so that's question number 7.2.3. Let's go ahead and just label that 7.2.3. All right, so a few things we have to look out for here will be the equation of how to do that, exactly what they're looking for us to do. Now, but I want you to pay attention here. What they want us to actually do is to calculate the hydroxide ion concentration. They're not looking for the concentration of this, all right, or the hydronium ion. They're looking for the concentration of the hydroxide, all right. So if we are going to get that and they've given us a pH, we need to remember the equation of the ionization constant of water, which is the concentration of H plus ion, or hydronium ion, if you may, or the concentration multiplied by the concentration of OH minus ion. Now, a Kw is a number which is already a constant. It's already calculated, and that number is equals to 1 times 10 to the power minus 14. So this number will be equated to what exactly the ionization constant of water is, which is your Kw. I'm sure you might have went through those in class. All right, so we have the H plus ion and OH minus ion giving us this. So I'm going to write that in an equation form. The H plus ion and the OH minus ion concentration will give us 1 times 10 to the power minus 14. So this is the equation that's going to work for me for this particular problem. Now, but notice they're looking for the concentration of the hydroxide ion. So I may now then have to divide by the concentration of the H plus ion, both sides of the equation, all right, or hydronium ion. Notice if you put hydronium ion there in my place of H plus ion, it doesn't make any difference, all right. So the concentration of OH minus will then equals 1 times 10 to the power minus 14 divided by the concentration of the H plus ion. The question then will be, what's the concentration of H plus ion, so that we can be able to figure out that number. Well, so we're looking for this and we do not have that, all right. So we have to figure this one fast. And if you look at the problem, they've given me the pH, and that's where my pH basically come in. So my pH is the negative logarithm, the concentration of the hydronium ion, all right. So I'm going to plug that the pH is a negative logarithm concentration of the hydronium ion is what I need to figure out. But you'll remember I've been given a pH. The pH is set to be 3.4. So in a position or in the place of pH, I'm going to place 3.4. That's going to equal the negative logarithm of the H plus ion. All right. Now at this point we're going to have to apply a little bit of mathematics. Our inverse of logarithm are exponents actually. All right, so we have to apply exponents here, and you're probably asking, what am I supposed to do? Remember, if you're solving for x, for example, and you're given 2 equals to log x to the base of, let's say, 3, for example. Now, in order for you to solve the x, what you need to do is you write this base, all right, which is the 3, and then these 2 you're going to write it as an exponent. So that's going to be the 2. Again, the 3 is the base there. So you keep it as a base and then you write that as an exponent. Now you can get rid of the log. So otherwise, x will equals to 3 to the power 2, which equals to a what? To a 9. We're going to do something similar here, except you're figuring what is the base here. If we don't know that the base, the natural base actually is a 10. All right, so we know that there is an invisible 10 around about there. Let me just make sure that that's clear. All right, so we're going to do pretty much the same thing, but again we're going to bump into another problem. We have a negative here, all right, and we're not looking. The inverse exponent of our logarithm is not an inverse of, for example, I may put it like this: an exponent is not an inverse of a negative logarithm. Is an inverse of a logarithm, so we have to pay attention to that. So I need a logarithm and not a negative logarithm. So I'm going to have to divide by a -1 both sides of the equation. That becomes then that, and then everything just pans out. All right, so that's going to be a log now, because I don't have the exponent, concentration of H plus 1, H plus ion. So now at this point, I'm going to have to apply what I did was trying to solve for x here. Let me just clear the space. All right, so we're gonna have 10, which is the base, an invisible base that was here, and then that will be to the power -3 minus -3.4, and then I'm gonna remove the log here. I'm gonna have the H plus ion. Now that will be my concentration of the H plus ion. Now, In order to find the concentration of the H plus ion, I'm going to go ahead and pull quickly the calculator and see where we go. All right. All right, so now with the calculator in place, we are looking to calculate the 10 to the power negative minus 3.4. So to the power negative or minus 3.4. That's going to give us a 0.00. I think I have 4 zeros after a comma. That's going to be if it's 4 zeros, is going to be obviously to the power negative 4. So I have 3.9 times 10 to the power negative 4. You can round it. 3.98 is also fine. 3.98 for more accurate, times 10 to the power negative 4 is equal to the concentration of the hydronium ion. All right, so you can put your calculator actually in scientific form in order for you to do this more accurately, but I've left it like that, which I can still write as 0.00039,810 and so on and so forth, if in case you're not sure of what you did right there. But I'm sure if your calculator is on scientific mode, which mine is not, it should be able to give you that answer. All right, now let's go ahead and just look at that. So the concentration is that. Remember, you may put the unit if you do want. The concentration is in mole per cubic decimeter. All right, so that's the concentration. And now that I have that concentration, I then have to put that concentration back here, and I will find the concentration of the hydroxide ion. So this is going to be 1 times 10 to the power negative 14 divided by 3,9. Let me round it to, let me have 3,98 times 10 to the power negative 4. All right, and if we do PyChart's calculator, we'll be able to find the concentration of that. Let me remove that so that you can see what we're doing. All right, so we're gonna go ahead and just punch everything in place. All right, so this is gonna be 1 times 10 times 10 to the power negative, or to the power exponent of a negative 14. And then I'm going to divide that. You can go ahead and just divide basically by the answer that we calculated. The concentration is, I'm not sure about that. Let me just punch it, 0.000, 0.0012 and 3. I think it's 3 zeros. And then I have 39, 39 and all of that. It's going to be a negative. It's going to be 25.64 times 10